Anybody ever heard the word kinetics before?
Yeah.
Do you have any idea what kinetics means?
It's like those little things that you like build.
Not connects.
Yeah.
Hey, now it's time to pay attention.
You said it was gonna be easy.
Yeah. Oh my soul.
Okay? So here is the definition of, you have the definition of kinetics in your notes.
We
Do you
have
know?
to like study
Kinetics is, here's your definition, you're going to want to put this in. So, some key words up here that are really going to tell us a lot about what this chapter is about. What does a rate mean?
the speed at which something is done.
Okay, so we are going to study how fast a reaction will react. We are also going to talk about the steps in which they react. I don't know if you remember me alluding to this last chapter when I said when you have a balanced chemical equation, it gives you the products and it gives you the reactants, but very rarely does it go straight from the reactants to the products. Did I say products to the reactants? Okay, I'll restate that. Very rarely do you go from your reactants to your products in one step. Usually there's a series of steps that happen along the way, which is what we saw when we did Hess's law last chapter, when we had 1, 2, or even 3 steps sometimes when we were doing the Hess's law. Okay? Now, what is the difference between an explosion and a minor reaction?
One gives off a lot of energy.
That's one thing. Very good. An explosion is going to give off a lot more energy. There is one other possibility.
An explosion is always.
Yeah, explosion will
An
probably
explosion
always be
doesn't
that.
have to
So.
be two
Yeah,
things. does it?
explosion.
Like,
Small.
like in a minor reaction,
It's like-
two things that react. But an explosion could just be one.
No. That's yeah. A couple of things. You probably won't figure. Probably won't. Think about what the purpose of this chapter is, and maybe that'll help you figure out what's another big difference between a big explosion. How fast the reaction is.
Oh, yes.
Things that react faster tend to be more vicious or vigorous. Things that react slowly, you're not going to see a lot of big booms, right? Okay? So, just because we have talked about the energy side last chapter, energy, again, just like we've been talking about, is not the only piece of the puzzle. Okay? How fast something reacts is also a major piece of the puzzle. So thermodynamics asks the question, can it react? If you add kinetics to it, the question becomes, will it react? Because last chapter we talked about how something is favorable, and I don't know if you remember, I know Natalie said it, I don't like the word spontaneity in last chapter because you have to add kinetics to it to figure out if it's spontaneous. Let me show you what I mean. I'm going to give you 3 examples here. 1, 2, 3. First example. Go and write these in. We got the oxidation of diamond. Our second is wherever. Burning methane. And our third example is next to them I'm going to have what their change in G values are. And what does the change in G value tell us?
Positive, spontaneous.
Not spontaneous again. That's where I.
Positive is favorable.
Yep. No. Negative is favorable.
Nah.
What you got wrong on the test? You might want to write that down somewhere if you don't remember it. Negative change in G is the favorable one.
So this is examples for what?
I will show you in a sec. Chill.
Whoa. So much salt.
Yeah, I just said, just a question. So this is example for what?
This is going to be how I'm going to use an example to show you how favorability does not necessarily mean spontaneous.
So last chapter is a joke.
No. Last chapter was a small piece of the pie.
I like pie. I had pie for breakfast yesterday.
What I'm saying is in chemistry, when you're studying things in nature and in God's creation, it's never as simple as you might think. There's a lot of factors that go into understanding chemistry well. Okay? So, from last chapter, from an energy and an entropy standpoint, all of these are what?
Favorable.
They're favorable, right?
Yes.
Okay? So, which means from an energy standpoint and from an entropy standpoint, they're likely to react. Okay? However, if I put methane on wood, will that react?
No.
No. So, this is the most thermodynamically favorable, but what has to happen for this to react?
Lit. Or
It
energy has to
needs
be
a
added to.
jump start of energy.
Is it spelled methane or methane?
Okay? Oxidation of diamond. What this simply means is diamond going back to basically carbon or charcoal. Did you know that oxidation of diamond is spontaneous? What that means is, ladies, when you get a diamond ring, your diamond will break down into coal spontaneously. The reason why you don't notice anything is because it is
Yep.
I don't know if I spelled it.
So when they say I got coal for Christmas, it's really
So you should go up to your mom and go, yeah, that diamond ring, it's just carbon. Just a
That's why.
You pay a lot of money for that carbon. Okay, but what I'm showing you here is,
If you press a person hard enough, will they be a diamond?
yes, I mean technically people decompose into carbon and other things, and so yes, it's very possible that your diamond ring you wear, ladies, was the dead
Conspiracy.
remains of some person.
Conspiracy.
Okay, now stop, listen. Okay, so here we got extremely favorable, but won't even react on its own unless we do something. Here we have pretty favorable, and it's spontaneous, but it's really slow, so we don't even notice anything. Yep.
Okay, I thought negatives were non-spontaneous. Wait, sorry.
Negative change in G means favorable.
Yeah.
But I'm saying, okay, so let me explain the difference between favorable and spontaneous right now. Favorable means from an energy standpoint and an entropy standpoint it's likely to happen, but just because I mix them doesn't necessarily mean they will react. Spontaneous means they come together, they react on their own.
Wait, so the negative and positive doesn't have anything
Not for G. If you take the G value with what we're going to learn in kinetics, we'll figure out whether something is spontaneous or not. Because this is really favorable, but it's not spontaneous. Just taking gasoline, putting it on wood does not cause a reaction to occur. However, once we give it a jump start of energy, it will react and continue to react without the help of us. Okay? Now this last one, if you notice, has the lowest favorability. But it is the only one that's spontaneous and does it fast. When you mix an acid and a base, they will react right away, very quickly, and with a lot of energy given off. So you kind of see that just looking at the negative change in G tells you a piece of the pie, but we have to start adding how fast and a few other things known as activation energy to explain number 2. Okay, so that's what this chapter is about. Adding on to last chapter so that we can understand what's spontaneity or what is spontaneous.
So the first one is spontaneous, but
So yeah, this and this are both spontaneous.
but
This is not spontaneous. This is spontaneous and fast, and this is spontaneous and slow. Okay, so I'm just showing you, they all have negative change in G's. So if we want to know if they're going to react, we have to know a few other things, which is what we're going to start filling in the pieces with in this chapter. So these are a few. I don't know if these are in your notes or not, but these are a few of the questions we are going to ask in this chapter. Okay, will the reaction occur? How fast is it going to occur? And what are the steps? All things that we will talk about in this chapter. Okay, and I just kind of talked about this. Even if your change in G is negative and favorable, it may not be spontaneous. Okay, and again, favorable means likely. Spontaneous means it will happen without any help. As long as they come in contact, the reaction will occur on its own. Okay. So here is another example of favorability versus spontaneity. If you have ice at room temperature, will it melt?
Yes.
Does it need our help?
No.
It's spontaneous. Okay? But we just talked about how just because we have gasoline doesn't mean it's going to spontaneously react. It needs some other factors, which we will talk about in this chapter. Okay? So, change in G tells us thermodynamically whether it's favorable or not. If we add the ideas of kinetics in here, we can determine whether a reaction is spontaneous. And that's where we're going as a big picture in this particular chapter. Oh no. We're already on that. Okay? Now some of this stuff here, we will actually talk about at a later time. I'm going to talk about this in a different lesson, a lot more. Okay, we have talked about energy diagrams. And I think it's on the, you might have, yeah, you have it sitting right in your notes right there. It's going to show on the board here in a little bit. What it shows is energy over time. Okay, shows the energy changes. Now I want you to, you have this, right? Is this in your notes somewhere? This is important. I want you to circle it, especially this. What does path dependent mean? What does path dependent mean?
It has to happen a certain way.
The path is important, right?
Yeah.
It's dependent on the path, right? Isn't that what path dependent means? So let me show you the difference. And I want you to put this in your notes too, next to the fact where it says kinetics is path dependent. I want you to write in your notes that thermodynamics is path independent. So kinetics is path dependent, and thermodynamics is path independent. Let me explain what I mean. Almost all of our equations last chapter were what minus what?
Products minus reactants.
Products minus reactants. All I was worried about is where I started and where I ended. Did we ever talk about anything in between the products or reactants? No. Okay? When we found the energy of the products minus the energy of the reactants, we never worried about the steps in between. Okay? Well, this is what methane burning looks like. From an energy standpoint, is this exo or endo? Exo. Reactants have much more energy than products. However, it's not spontaneous because of this.
This energy is added.
Okay? So, what this is called is the activation energy, which we will get to later on in this chapter. This is the spark's purpose when you're burning something. You have to give it an input of energy so that it can overcome this little hump. And then as soon as it gets over that hump, Does fire burning or methane or gas burning have any problem continuing to burn? No. It's on the downhill slope after it gets over that little bump, isn't it? Doesn't need any help after that point. Okay, we're going to talk much more about what that looks like in the following lessons. I'm just kind of giving you a big picture here along the way. Okay? So I would probably say that this is thermodynamically favorable and spontaneous. This would be like acid and bases coming together. I don't need to give it an input of energy. As soon as it starts coming in contact, it will react and continue to react. This one's thermodynamically favorable. Okay, and will happen fast, but only once you've overcome this little hump, which is what the purpose of a spark is when burning something. Okay. Last thing, I think. Does that make sense, everybody? I don't want to go too fast. Yeah, I do want to make sure that you guys grasp that. I know I haven't talked so much about what that hump is. That'll come at a later lesson. But does it make sense how the ball would roll down this without any help? And then the ball will not roll down this without a little help? Okay, that's the difference between, both are favorable, right? From an energy standpoint, the beginning has more energy than the ending. Both are favorable. This one's spontaneous because it doesn't have to overcome this little hump. And the one on the right is not because it needs a little jump start or kick to get it to react. Okay. Last thing, collision theory. There are three things needed, okay, for a reaction to occur. Okay, you probably have guessed what the first thing would be. It's called the collision theory, but this should make sense. Is a reaction going to occur if they don't collide? No. Things have to collide for bonds to form, don't you think? If two individual atoms never come in contact, is a bond ever going to form? No, never. Okay? If you never come in contact with your future spouse, are you ever going to get married to that future spouse?
Skype.
Okay. To me, that's contact, because you can see each other. Okay?
I think Stu put
Now.
evidence that that was a word.
What? Okay, yeah, I'm not even going to ask.
No.
Okay, the second thing that must happen is you've got to collide. Those collisions have to have enough force. For example, okay, you've got reactants that are bonded to each other a lot of the times, right? Like H, like when I'm reacting oxygen gas with hydrogen gas to produce water. I have bonds there, right? We said those bonds have to what? Break. In order to break, they must collide into each other with enough force. The higher the force, the more energy they have to break the bonds. This right here is part of the reason why what an input of energy does for something to burn. You're giving it enough force so that it can break the bonds and roll down that hill over the hump. Okay? First thing, gotta collide. They must have enough force and energy. If they don't have enough force and energy, the bonds won't even break. It doesn't matter that the formation of bonds gives off a whole slew of energy. If you don't have enough energy to break the bonds to begin with, are you ever going to get to the formation giving off a ton of energy? Third thing. Okay, collisions with proper orientation. What this means is that atoms or compounds must collide in the right way. Like if you wanted an oxygen and hydrogen to bond, you wouldn't want two things colliding so that the oxygen and hydrogen are not even coming into contact. And I'll show you what that looks like with a little demonstration. But if, let me see here. I'm trying to think of a good example. If I had HCl reacting with water, I'm almost done, guys. If I have HCl reacting with water, and the chlorine hits the hydrogen, but I want the hydrogens to hit each other so that I produce something known as hydronium, which is H3O. If they don't ever come into contact when they collide, are they going to react? No. So three things must happen. Yes, they need to collide, but if they don't collide the right way or oriented the proper way, they're not going to react. And if they don't have enough energy, they won't react. So, quickly,
Is this physics? We just.
no? Okay? So this is just kind of talking about proper orientation. He's laughing, why?
Because they missed.
Oh, he hit right on the bullseye, but what?
They hit it wrong, so it didn't.
Not enough force,
I've
okay?
been in one of those.
Plenty of force, but
Proper.
not properly oriented. And you can imagine the last one. Oh. Properly oriented. Was there a collision?
Yeah.
Was the collision properly oriented?
Yeah.
Was there enough force?
Yeah.
Yes. Same thing here. Oops. I'm gonna go back and show you this. This is a better example of what particles are gonna look like. They come in, they collide, but they didn't have enough force.
Oh,
Okay?
so sad.
So they were properly oriented. These things needed to collide, okay? Which they did, but they weren't what? Didn't have enough energy or enough force. Here they had enough energy and force, but notice what didn't come into contact.
The red thing.
These two things did not come in contact, so because they were not properly oriented, they collided, they had enough energy and force, but they did not react because they weren't properly
It's like
oriented.
an egg with a pepperoni sticking out.
Okay, and then lastly,
Oh.
Oh, shoot.
they collided. They collided with enough force and energy, and they were properly oriented, causing a what to occur?
Reaction.
Reaction. That is the collision theory. You guys may leave.
That was close. I was jumping it back and forth. Oh, man.